So next we've got Mal McMillan.
Okay, thanks very much. Hi everyone. So my name is Mal McMillan. I'm from the Centre of Excellence in Environmental Data Science at Lancaster University, and also the UK Centre for Polar Observation and Modelling. So my background, I guess, is polar Earth observation. So I guess in this talk I'll be bringing a bit of an external perspective in terms of probabilistic AI, as someone who's very much not an AI expert or an AI specialist, but someone that kind of sees the opportunities hopefully there in terms of how it can be, how it can transform some of the workflows that we do. And indeed, within our group, we've been starting to look at how we can integrate some of these into our satellite processing chains. So acknowledge my co-authors there, especially Joe Phillips, who's at the back, who's responsible for a lot of the work we've been doing in this space, and I guess a number of the different funding agencies that have supported this work. So I'll talk about polar Earth observation because that's kind of the area that I specialise in, but I hope that a lot of the kind of the techniques and approaches that I talk about, you'll kind of see are translatable to other kind of areas of environmental science where Earth observation data sets are useful. So in terms of the scope of my talk, I kind of split it into three main parts. I'll start with a brief bit of introduction, both in terms of the kind of the scientific context, so kind of the need or the kind of the I guess the state of the climate that we operate, and also the drivers in terms of the wealth of data that we have available to us. I'll then talk a bit about a specific example where we've been thinking about how we try to redesign or rewire kind of our conventional satellite processing chains, looking to bring in kind of machine learning elements. And then I'll finish at the end by just a bit of a future outlook where I'll touch on a number of different areas where I think there's potential for development, and I hope that it might trigger some ideas and some collaborations afterwards. As I mentioned at the start, I'm not an AI expert, so it's a bit daunting to be amongst such people here. But as I say, I hope it brings a helpful perspective and can help to kind of trigger some of the interdisciplinary collaborations that we really need to actually exploit the wealth of data that we have available. But please be kind to me in terms of questions. So in terms of context, I guess I probably don't need to say it, but the polar regions are undergoing kind of unprecedented changes in climate at the moment, and those changes have kind of global consequence in terms of their impact. So as climate warms, it melts ice both at the surface and at the peripheral boundaries of the ice sheet. And we know that this ice melt or this ice loss has kind of quadrupled since the 1990s. So we're in a position now where about 40%, almost half of current sea level rise, is coming from the melting of ice sheets and glaciers. And we expect that to continue. We expect several tens of centimetres of sea level contribution from these factors by 2100. And given that over 200 million people live within about a metre of current sea level, this is obviously a significant challenge. So how do we monitor, how do we measure these remote regions? So we use satellites. They're really the only way to actually do comprehensive monitoring of these vast and inaccessible regions. Like many fields, I guess we've seen quite significant increases in the volumes of satellite data since kind of the start of the 21st century. These are driven by a number of factors, so increasing volumes, high resolution or higher resolution data, but also the advent of more kind of operational programs. So this is just a slide of the kind of data volumes just from the European Space Agency. Obviously, that's compounded then by data from other space agencies such as NASA. So why are these satellite data important? Well, I guess a number of reasons. So firstly, they allow us to quantify sea level rise over the past few decades. That's what you can see here is the embed assessment, which is an assessment of different satellite methods for estimating sea level rise from ice sheets. They also give us a better process-based understanding, so they allow us to get better physical representations of the processes through which ice sheets interact with a changing climate. And they also allow us to both act as boundary conditions and also calibrate and test numerical predictions going forward, which is what you can see here for a number of different modelling scenarios or future climates. But I guess the question is, do we really currently have in place the frameworks that allow us to make full use of the information content in these satellite data? And I guess what I'll aim to show through some of these slides is that I don't think that that's the case currently. We have huge wealth of satellite data out there, but we haven't quite caught up in terms of how we process and we extract information from those data. So when we think about AI for Earth observation, we saw some really nice examples in the previous talk. A lot of the time we're thinking about image classification tasks, and the use for, or the motivation for AI coming into this field, I guess, is driven by a number of factors. So need for automation, need for scalability, and a push towards more operational products and services. So this is an example here of mapping all of surface hydrology over the Greenland ice sheet. Again, we're operating at around 10-meter resolution. We're doing this for an area of millions of square kilometers, and we're trying to do that on a monthly time period. And so obviously there's a big opportunity there for kind of AI techniques to help us and assist us in that process. But I think what I wanted to spend a bit more time on in this talk is kind of thinking not just about how we use it for kind of classification tasks, but how we use it more in terms of actually how we organize or how we arrange our processing workflows for the satellite data. And in particular, thinking about that probabilistic element of how we actually capture the inherent uncertainty in those observations. So what I'll talk about kind of as a more in-depth study is how we're looking at trying to rethink or rewire satellite processing chains. So this is work that's been done by Joe at Lancaster University. It's kind of a proof of concept study, so we're kind of very open and welcome suggestions on ways that we could develop the approach, things that you can see could be improved going forward. But essentially this is motivated by thinking about a particular type of satellite data, so satellite altimetry data, which is kind of data that allows us to build up those long-term observations of ice sheet change and sea level rise. So it's a relatively simplistic measurement. It measures the surface of the ice sheet through time. You build it up through a sequence of tracks as the satellite orbits. And then by measuring changes through time, we can estimate areas of the ice sheet which are gaining mass and the areas which are losing mass. And the methods that we have for processing these kind of data have remained kind of largely unchanged throughout the past kind of 20 or 30 years. And they're limited by a number of factors. So they're limited by assumptions and the fact that we're not really exploiting the full information content of the data. So if we think about kind of a generic kind of workflow of how we use satellite data, this is obviously hugely simplistic, but we acquire data from the satellite, we downlink that to ground stations, then we apply some processing steps to extract geophysical information from that satellite, and then hopefully that drives some insight into our understanding of the environment, and then some action. So if we focus in on, I guess, the processing step, which is, I guess, the area that we're most interested in, we can think of that as acquiring relatively raw satellite data, so the information that's downlinked from the satellite itself. And then typically this will go through a number of kind of modules or tasks in series to convert it into some kind of geophysical parameter, ideally with an estimate of uncertainty on that. And so that might be a set of corrections to account for things like atmospheric conditions that change the signal as it passes through it, and also transformation and reduction in terms of the data content to provide it, to get it through to kind of the geophysical parameter in the end. And all of those are subject to assumptions and auxiliary models, which are very hard to quantify the uncertainty on those as you move through the chain. So the question we ask is, well, actually, although that's the way that we've done things for the last 20, 30 years, could there be a different way of doing that which looks to kind of address or circumvent some of those assumptions that are in the data? And I suppose to have more of a data-driven approach that really respects actually the information content in the data itself. So what do the data actually look like? So this is just an animation where we're making landfall over Antarctica. So the top plot kind of shows a 3D view with the purple dot showing where is illuminated by the satellite at any particular point. Then in the bottom left you have the raw signal or the waveform that's acquired by the data. And then in the bottom right you essentially have a slice through the topography that's being measured across the satellite swath. So the purple surface that you can see evolving through time is the topographic surface. And so the question we want to ask is, can we essentially train a model to predict that topographic surface from the raw waveform itself, rather than passing the waveform through a set of kind of different processing steps? That allows us, or that forces us to think actually about what we're actually measuring, so what the satellite is measuring. And so what it's actually measuring is I guess the backscattered power from the surface of the ice sheet as a function of time. So it's a 1D measurement. And so that means that each waveform actually corresponds to a distribution of possible surfaces on the ice sheet. And so with conventional processing, we would apply some assumptions to try and collapse that distribution. What we're asking here is actually, can we try and just estimate that distribution itself? So can we train a model to learn the underlying distribution of that topography? So the way we do that in very simple terms is that we train a model based on reference or ground truth elevation data to be able to predict for any particular waveform or detected signal what the topography of the surface is there. We don't just try and estimate one single topography, but we try and estimate quantiles on that distribution of topographic surfaces, so the 5th, the 50th, and the 95th% quantiles. And we try and estimate the uncertainty on each of those quantiles by performing an ensemble of models. So you can think of that a bit about trying to split out epistemic and aleatoric uncertainty. So we're trying to get at the aleatoric uncertainty on the estimates through a kind of a quantile regression approach, and we're trying to get on at the epistemic uncertainty by performing an ensemble of runs. So we can then train a model over a certain part of Antarctica, and then we can evaluate it on an unseen part of Antarctica to see how well it can do at estimating topography. So what does this look like in practice? So the top plot is an example waveform that the model has never seen before. So essentially this tells us about the power that's returned from the surface as a function of the time it takes to get back to the satellite. And a standard approach to processing those data would be to apply a number of assumptions to try and extract a single point from that waveform and convert that into a single point of the ice sheet elevation. But clearly that's throwing away information, and it also has a number of assumptions that are hard to characterize in terms of the impact on the overall uncertainty. And so what our approach is doing instead is saying, if we give a model this waveform, can it tell us what the distribution of topographic surfaces that could have produced that waveform could be? And this is the kind of output we get. So in blue, we have the unseen topography. So this is the topography that actually created that waveform. And then in orange we have the predicted quantiles from the model of what it predicted as being the topography. And so I guess really importantly, we don't just get an estimate of the topography, but we get an estimate of the relative uncertainty on that topography. Ultimately, I guess we're interested in terms of actually how well can this kind of method do at comparing it to the current state of the art. So this is an example now where we've processed 5 years worth of data, and we use that to estimate the elevation change of the ice sheet over a region which hasn't been seen before. And essentially what we find is that it gets pretty close to being able to reproduce kind of other state-of-the-art techniques. So I guess to wrap up this part, in terms of broader perspectives, what's the point, or what have we gained from this kind of alternative approach of how we process the data? Well, we get firstly enhanced data retrieval. So for every waveform, we get around 100 times more estimates of elevation than kind of through conventional approaches, and that allows us to get better spatial temporal coverage. We also do more with less, so I haven't really touched upon it here, but we're actually able to strip out some of the information that's acquired by the satellite and still get comparable performance. I guess within the context of this workshop, I think a key point is that we feel like it does a better job at respecting kind of the inherent uncertainty or the aleatoric uncertainty within the observations themselves. And ultimately that means that when we propagate through our processing chain, we get a better estimate of uncertainty actually on the climate parameters that come out at the end. And then I think more conceptually, it kind of demonstrates how we might start to rethink how we process satellite data, from going something where we're essentially passing through something through a series of kind of forward models or through a series of processing chains, to something where we're more trying to just extract information from the data itself without relying on assumptions and approximations. So in the final part of the talk, I just wanted to go through a few kind of the future opportunities that I see in terms of the use of machine learning and probabilistic AI within Earth observation. I won't go into in too much detail on any of them, but it's more to kind of paint a picture of kind of landscape of things that I think would be great to work on in the future. So I've kind of split them into going forwards and backwards in time. So going backwards in time, I think that there's a lot of potential to look at mining information from historical data. So going back to look at old data and what we can actually learn from it. And then going forward in time, I think there's a lot of potential for looking at elements such as anomaly detection in streaming satellite data, and also forecasting, so predicting over relatively short time periods future change. And if I focus on that first element first, on the future element first, so I guess this is motivated by the fact that we're essentially getting to a point now where we have what's close to kind of movies from space. So they have a very slow sampling rate, but we are getting systematic, regular sampling of in this case, areas of the ice sheet. And so we should really be thinking about how we actually process and analyze that data as it is streamed in. And that leads us to think about things such as short-term forecasting and anomaly detection, thinking about how we integrate things such as video surveillance techniques into our processing chains. So to give, I guess, just a single example as to why that's needed, why we're currently missing this element from our processing chains. So I'll take you to the far kind of north of Greenland, an area called the Harder Glacier, which is where we have a number of glaciers that are draining into a particular fjord system. So this is a Sentinel-2 image. If we focus in on this region here, then what we actually see, if you look closely, is an area of kind of fracturing and crevassing of the ice sheet. This is quite a sizable area, so about 54 football pitches in size. It's important because it tells us about a new process that we didn't understand or realise before, and that's actually where water from underneath the ice has fractured the ice surface and come up and kind of erupted out of the ice, and that's not a process that we knew about before. But within the current context, I think what's really important is we didn't detect it for 5 years. So it's there, it's obvious, it's large, but we didn't detect it. And why didn't we detect it? It's not because the data don't exist. So this feature has been imaged by optical data, by SAR data, it's visible in high resolution digital elevation models, but it's because we don't have the frameworks that allow us to look and monitor over the whole ice sheet on in-streaming data and detect anomalies as we go. And essentially the data are there, but we haven't caught up in terms of our processing pipelines. So this is something, I guess, that we're looking at in a fairly kind of proof of concept sense, in terms of can we design kind of approaches borrowing on work from kind of video surveillance to actually start to analyze and detect anomalies in data assets acquired. It's early, we haven't really started yet with it, but I think a probabilistic component will be really important in this because as was mentioned in the previous talk, we don't want just a deterministic prediction, we want some estimate on the uncertainty or the confidence that there is in those predictions. We can also think about future platforms. So I've talked a lot about satellite data, but we're also thinking about other platforms that might exist in the next 5 to 10 years. So this is one example, which is a HAP system, so a high altitude pseudo satellite, which essentially can fly in the stratosphere. It can be solar powered, so it's low carbon, and it presents the opportunity to essentially to persistently monitor particular areas. So once this kind of technology becomes more developed and more mature, we will literally be able to get kind of high sampling movies from space, and so we need to make sure that our systems, our processing chains are kind of fit for purpose to be able to exploit these kind of new streams of data as they come along. If anyone's interested in this, we're also thinking about what kind of payloads could go on a system like this, so please talk to me about that afterwards. So alongside, I guess, anomaly detection, there's also thinking about data-driven forecasting. So Scott mentioned it a bit in his talk, and he's also other work from his group in terms of it within the context of sea ice seasonal prediction. But we're also starting to look at trying to forecast based on data, on in-streaming data, things such as icebergs calving, and looking at what sort of lead time, so how far in advance can we actually detect it. And again, I guess the probabilistic element is really important there because we want to know the confidence in the prediction in terms of how confident we are in terms of when an iceberg or something like that might occur. And then finally, I think we shouldn't forget historical data. There's a wealth of information in there which just like, or which we haven't fully exploited, I don't believe. And so I think there's a lot of work that we can do around actually taking kind of new data and training models to then run through historical EO data to extract information. So in this case, these are all subglacial lakes in Greenland, images of them from various sensors. And I guess it's an area that's very, or quite great interest to try and understand whether we can detect these kind of features more automatically. So just to summarise, so I'd say from an EO perspective, I don't think yet we fully understand the full potential of AI in terms of its ability to transform EO workflows and what that will actually mean in terms of the impact it has on downstream users and stakeholders. I guess I've shown a few early examples, but I think we're still kind of learning, and we very much welcome kind of feedback or collaboration in terms of how we might develop these kind of systems for processing satellite data, so going from the raw data through to the observations that models then require in a more kind of data-driven approach. I think embedding probabilistic reasoning is really important. We need uncertainties, we need that probabilistic component in order to be able to make informed decision making. And ultimately this needs collaboration between data scientists, statisticians and the EO community to think about how we kind of design those systems. So if that's of interest, then I'd welcome chatting to you afterwards. With that, I'll finish there. Thanks.